Yes, yes. Today we're going to do kind of an interlude chapter. We may finish the chapter. We're not scheduled to finish chapter today, so we'll see how we go. We're going to be talking about the stuff between stars. So we call that interstellar media. So what have we talked about so far? We talked about the sun. What else have we talked? I'm talking about the whole semester. What have we talked about, class? The sun is the most recent. Okay, the solar system.
Outside planets.
The planets, the things that are inside the solar system. We also had, besides planets, we had moons, and we had asteroids, and we had comets. And we've talked about observing the sky, the ways we measure things in the sky. And now we're going to be moving into, well, the last chapter, I guess, after the sun, we talked about other stars. We talked about things like how we classify them by their size. We determine their size from that HR diagram. Oh man, I was going to show a bunch more HR diagram pictures. Let me just load up the last lecture. Not even start with today's lecture. Finish the HR diagram pictures. Whoops, from the last lecture, because those are very cool as always. Open astronomy 20. So we learned about we can determine the size of a star by looking at its luminosity class, or its luminosity, not class, its luminosity and its temperature. And we do that with the HR diagrams. So HR diagrams were down here near the end. Remember I said I had like 7 of them, and we had so far seen, that's the first one, so I'll start there. Or maybe I won't start there. Maybe I'll click forever and get there. I guess I pressed the wrong button for starting where you are. Okay, so this is where we start with the HR diagrams. I said you're going to have this memorized for the next quiz, which is probably going to be on Monday. So you need to know luminosity. Low luminosity is the bottom, high luminosity is the top. Temperature, low temperature is the right, high temperature is the left. And then I showed that the white dwarfs were down there in the bottom left corner. The main sequence was this region here that I haven't described what makes it the main sequence. And then we had the giants out here. How do we know they're giants? Because of this luminosity relationship that says that the radius can be solved as a function of luminosity and temperature. That's a temperature squared there. For some reason, the 2 got demolished. So you can make a graph that separates, or these green lines show you the sizes of the stars. So small stars down here, large stars up there. Now we get into what are the luminosity classes. The classes based on how much light a star gives off is what luminosity class should be. If you look at this, you can see some ideas of how they're separated up. Up in the top right corner, you have Betelgeuse and Antares. I said it in the last class grade, but what should we call those things? What color are they? Red. And they're really large, so giants. So those are red giants. Then we have, we've already identified these dwarfs. These here, they're still large, and so they're still giants. We'll talk about the different classes here in a minute. And then this main sequence, note that the sun, of course, is a star. This green line here is 1 solar radius. The sun has a radius of 1 solar radius. The temperature of the sun, come down here, and it should be 5,800 kelvins. The luminosity sun, you come over here, it should be 1 solar luminosity. Right? We use our sun as the reference point. Oftentimes over here, instead of mirroring these, they will put the absolute visual magnitude. The absolute visual magnitude is a measurement of the luminosity calibrated to be the brightness you would have in apparent visual magnitude if you were 10 parsecs away. So now let's get to the luminosity classes. And first, I have this interlude, and I will warn you right off the bat, the number here for that fit is not universally agreed on. Our textbook goes with the luminosity is approximately equal to the mass raised to the 3.9 power. Now that's saying luminosity in solar luminosities and the mass in solar masses. So of course for our sun, M is 1 solar mass, 1 raised to the 4th power is still 1. And so L is 1 solar luminosity. So if you have a more massive star, it gives off a lot more light. In fact, if you have a star that's 2 solar masses, twice the mass of our sun, rounding that exponent off to 4, how much more light does it give off if it was twice the mass? 2 times 2 times 2 times 2 is 16. So it'd give off 16 times more light if it had twice the mass. Why? Well, one reason is it's going to be bigger. So it's going to have more surface area. But that doesn't count for everything. What else is it going to have to give off 16 times more light? Surface area is 4 times greater. What else is it going to to get 16 times? It's going to have to be hotter as well. It's going to have to be, let's say 1.4 times hotter, as well as twice the radius. The reason I warned you, this here is a picture from one textbook, and it says the fit is 3.5 for the exponent. This is the fit from our own textbook, and it says 3.9. This one draws the straight line, that doesn't draw a straight line. I suppose it depends on what you pick. This relationship is only for main sequence stars. And you might wonder, how in the world could they have a difference in these? The main sequence, I'm going to look at this one. I swear I did a better job with those lines. Well, they're indelible now. The main sequence is not a single thin line. It's got some width to it. And so you have stars that fall different places for the same mass. So that's why it's not going to ever be a perfect fit that everyone agrees with. So here are luminosity classes. The luminosity classes, I have 2 different pictures here from 2 different sources. This one here, there is something on top of it. I guess I have a title on top that makes it so you can't really see it. But these here are bright supergiants. 1A equals a bright supergiant. So those are the things at the very top of an HR diagram. And note that those are going basically across the entire range of temperatures. Right, in our previous picture, we said the red giants were up in the top right. Red giant is not one of our luminosity classes. Bright supergiant is a luminosity class. And then type 1b is a regular old supergiant. So Roman numeral 1s are supergiants. 1a are bright, 1b are just regular. Then you have Roman numeral 2, bright giants. So Roman numeral 2, it shows them as here, or here it's got a little curvature to it. 3 are giants. So 1a was bright supergiant, 1b was supergiant. After that, we don't use an A and B. 2 is a bright giant. 3 is a giant. And then we get to 4, and 4s are subgiants. So the 4s, and once again, it depends on which one you look at. The 4s are more down here, or it shows them here. Notice this shows them extending up close to the main sequence. So I better circle the 3s just so we can have them all delineated. So Roman numerals 1a, 1b, 2, 3, and 4 are all some type of giant. And the closer it is to 1, the bigger it is. It's also going to be giving off more light, higher luminosity, the closer it is to 1. Then we get to Roman numeral 5. Roman numeral 5 is the main sequence. This shows up with really great contrast on my screen. Not so great on yours. And now I'm going to talk about what's special about the main sequence. The main sequence is where a typical star spends about 90% of its life. Or to put it another way, about 90% of all the stars we observe are on the main sequence. You see how those two correlate. So the main sequence is where most stars are. That's where a star will be with its luminosity and temperature relationship while it has a stable fusion of hydrogen into helium in the core. So main sequence, stable fusion of hydrogen to helium in the core. Off main sequence is something else, which is generally death stages. So these other categories, the Roman numerals that are less than 5, are death stages for a star. And then the white dwarfs, which don't have a Roman numeral, are dead. They're no longer stars. They used to be. So these are the luminosity classes. How are luminosity classes determined, you ask? You asked, right? Glad you asked. They're determined by looking at the spectra. And I don't remember if I have the slide here for that or not. This might be the end. Nothing is happening, that's for darn sure. Nope, I do have it. It just wasn't working. They determine it by looking at the spectra of the stars. If you have a star that is relatively small, you're going to have a actually much higher pressure in the near atmosphere where you see the absorption lines. And that higher pressure means you can have a lot more collisions between the atoms. That more collisions between the atoms means the energy levels are going to be more fuzzed out. And so you have broader absorption lines. So they actually determine the luminosity class by looking at the absorption lines. Now this says a white dwarf. White dwarfs have essentially no atmosphere to begin with. But they have very high pressure near the surface where that essentially no atmosphere exists. So they have very broad absorption lines. Whereas if you have a blue giant, you have very narrow absorption lines. So it's by looking at the width of the absorption lines that they determine the luminosity class. Now, aren't you glad you asked? Think this is going to work this time? Yes. So here is the cliff notes. The different luminosity classes: bright supergiants, bright giants, ordinary giants, subgiants, and main sequence. Put this together and you describe a star with its spectral class and its luminosity class. Remind me, because you know I'm old, what is the spectral class? What does it tell us about a star? I know you guys know this answer. The temperature. The spectral class tells us the temperature. What is the spectral class for our sun? G2. I trust that's what you're saying. Okay. It's a G2. G0 would be the hottest in the G class, about 6,000 kelvins. We're about 5,800 kelvins, so we're a little bit below G0. We're a G2. You should learn for the next test the rough temperature ranges for each of the spectral classes. Don't just memorize, oh, be a fine gal, kiss me like this, yo, but also memorize the temperatures. So our sun is what's the luminosity class for our sun? Main sequence, right? We saw it on one of the graphs when I pointed it out, one of the HR diagrams. But we also could have said, nobody said anything about our sun dying. It probably is in that 90% of its stage where it's not dying. So the sun is a main sequence G2, so we call it a G2V. That's how we describe our sun. It's G2V. So if we come back and we look at this HR diagram here, which one's the one I wanted? Okay. If we look here, what would Betelgeuse be? Betelgeuse is right about here. Okay, it's definitely going to be 1. Is it A or B? We could be more exact if we looked here. Yeah, this is the best one. Betelgeuse, is it 1A or 1B? Actually, it's A. It's in the top bubble. So Betelgeuse is a 1A, and then we can see here it's in the M. So Betelgeuse is a 1A, or is it M something? I don't know its number. Probably like an M3 1A. I'm guessing on the 3 just based on where it lies here. And what about Rigel? It's like a B9 1A. And so you can go through and you say, Arcturus is probably a Roman numeral 3 maybe. And so it'd be like a K0 Roman numeral 3. And of course, this is not exact. We don't have everything we need here. You look at more detailed information to get those right. Leslie had a question.
How do you see the Roman numerals? Like
1, 2, 3, 4.
No, I'm saying like you just look at it and you know that it's on the top.
Okay, from the positions right here. So for instance, if we looked here, we see 1, 2, 3. Actually, for Arcturus, that should have probably been in. It's hard to tell here because it has these 2 are the 1s. This is the 2, this is 3, and this is 4. Is Arcturus in the one I circled or the one right above it? It's probably in the one right above it. It's probably a Roman numeral 3. I should have used Roman numerals now, shouldn't I?
Yeah.
Do you guys know how Roman numerals work? Yes? So 4 doesn't confuse you, right?
Yeah.
IV. If you put the smaller number before the bigger number, you subtract.
Okay, so we just know that the top one is those first 2 spaces there.
The top 2s are I's. This is IA and IB. Is that what you're asking?
Yeah, you just know that they're in that category. It's in the Roman numeral 1, both of them.
Well, yes, but one's 1A and one's 1B. Those are different.
Yeah, but I'm saying like Roman numeral wise, they're both the 1.
Yes.
But then the 2 different parts there.
Yeah. Okay, so that's how we classify stars. Now we can go on to the lecture that I had started before I realized, wait, I didn't finish all the HR diagrams. So now we're talking about the interstellar medium. We've learned a lot about astronomy. We've learned probably everything and more that most people think of when they think of taking an introductory astronomy class. Teachers don't think of that as the introductory astronomy class. The teachers think of this stuff that we're going to as the most important stuff. And of course, what am I? I'm a teacher. I think this stuff is really important that we're getting into. So, the interstellar medium. Here's a pretty picture. I'm going to turn off the lights because it's just better without the lights. Somebody's been messing with my light switches again. What we see here on the left is what we call an open cluster of stars. The Pleiades, one of the things that you're going to have to point out for astronomy lab final, is an open cluster example. Open clusters are clusters of stars that are not super densely packed. And we'll learn about why they exist and so on at a later time. And then we have on the right a cloud of gas. A cloud of gas in astronomy is called a nebula. Now, how thick are these clouds? A very reasonable question. The average density for a cloud in the interstellar medium, that is outside of the solar system, in the galaxy, is about 1 atom per centimeter cubed. So you take a little centimeter cubed, a box this big, and you have 1 atom in each of those boxes. So in this room, we'd have, thousands of molecules if we were in the interstellar medium. Seems like a lot, right? Until you realize that in this room, we have billions times billions times billions of atoms. You would have about 10 to the 19th atoms in that same volume here in the air that we tend to think of as pretty empty. So the density of the vacuum of space is far fewer atoms per square centimeter than anything we can achieve on Earth. Our very best vacuums on Earth are roughly equivalent to the densest clouds in the interstellar medium. So what we consider a vacuum that's nearly perfect on Earth would be a thick cloud in astronomy. So just have that for reference as we go through this. They are clouds, but by any Earth-based perspective, they're very, very thin clouds. And then we're going to talk later about the sun's local hot bubble. And yeah, we'll get to that. It's kind of funny, I think. Nebulae are cool things to view. This picture shows 2 examples of nebulae. You have an emission nebula. Emission nebulae are pinkish in color. They're pinkish in color because they're producing light primarily from hydrogen emission lines. Then we have the blue. Where do you find the blues here? We have blue here, 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 here. What do you see in common with all of those regions that have blue? What?
I just was talking about like the center, it's like really white and the outside has like...
Okay, the center is really white. That is the key. What's the things that are making bright light in the sky? Stars. So the reflection nebulae are close to stars. Or at least as we view them, they're close to stars. So that's an important hint about what's going on with the reflection nebula versus an emission nebula. Something to do with the location being close to stars. So these reflection nebulae are actually blue in color because of scattering, Rayleigh scattering, exactly the same reason the sky is blue. The sky is blue because light from the sun, just like this is light from a star, comes and hits scattering centers on Earth. That would be the molecules in the atmosphere. Here it would be molecules in those clouds. And if those scattering centers are smaller than the wavelength of light, then the light scatters with blue scattering much better than red. So the star light is basically white, and then the blue light gets scattered out in all directions. And so if we're looking directly at it, we're going to see it without the blue. And if we look close to it but not at it, we're going to see the blue light that was scattered away. So that's what's going on there with the emission nebulae. Now, with the reflection nebulae. It's scattered. Emission nebulae is when you have a cloud of gas that has atoms that are excited to the first energy state, or first excited state, the second energy state. If they're in the first energy state, no luck. But if they're excited to the second energy state, then you could have electrons absorbed and come back down. Or, more likely, you have hydrogen atoms that are at least 10,000 kelvins and have been ionized. They call ionized hydrogen atoms H2, and that's H with a Roman numeral 2. H2 means that it is, H1 would be a neutral atom, H2 is singly ionized. One electron was removed. Hydrogen atoms only have one electron. So you can only have H1, neutral hydrogen, or H2, singly ionized hydrogen. And so that's where electrons have been removed. Well, if electrons have been removed, any electron that happens to come by will then fall down, be captured, fall down to low energy level, and give off hydrogen emission lines until you have a collision or absorption of UV light that ionizes it again. So these red emission nebulae actually tend to be regions that are like 10,000 kelvins, that are H2 regions where you have hot gas. The Orion Nebula, now this is kind of an odd picture of the Orion Nebula, but the Orion Nebula is one of the things that when I started teaching astronomy was the coolest thing in astronomy. It was supplanted by the Eagle Nebula. The Orion Nebula is a region where you have star formation occurring. You have lots of gas, lots of thick gas clouds. We're going to look later at the Orion Nebula, look at the Horsehead Nebula that's part of the Orion Nebula. So you have in the Orion Nebula lots of new stars forming, lots of both the blue reflection nebulae and the red emission nebulae. You have a lot of dust, which absorbs and gives you the third kind of nebula, a dark nebula. And so if you look here, you see this region right here, it's all dark. That's because, it's not because there's no light being produced, it's because there's something that's blocking the light, and that's a dark nebula. Interstellar reddening is an interesting phenomenon. And there are two things that you can talk about for reddening. One is a Doppler shift reddening that occurs because of motion of a star or the expansion of the universe. And one is this one here, where you have light that goes through a cloud. And as the light goes through a cloud, you're going to have scattering, much more of blue light than you have of red light. So what comes through is reddened. It doesn't have more red, but it has less blue. Hence, it looks redder. So that's what we mean when we say interstellar reddening. This was actually discovered when people were looking at a binary galaxy. We just finished talking about binary galaxies. Or not galaxies. Oh, man. Stars. Thank you. Binary stars, where we have two stars going around each other. And so they're looking at the Doppler shifts. Remember from the last lecture, you have Doppler shifts going back and forth. Except for they saw Doppler shifts going back and forth, and then others that just stayed constant and didn't change. They're like, wait a minute. How is it that some things are not changing and others are? They also noticed that the ones that weren't changing were very thin lines. Very thin lines, meaning that, just like we saw with the luminosity class, it must be regions of low pressure gas that are producing these. So they hypothesized, and later it's been confirmed, that what they were seeing actually was a gas cloud between us and the binary system that was absorbing lines. And so that was evidence of, yes, there's these gas clouds between us. Now, what is the universe made out of? The interstellar media, which, the gases, that stuff, makes up around 15% of the mass of stars in our Milky Way galaxy. Okay, just to throw something out there to make you go, what? About 95% of the mass in our Milky Way galaxy is what we call dark matter. And dark matter means we don't know what it is. You look at all the stars, all of the dust, you combine all of that mass, and that's only 5% of the mass in our Milky Way galaxy. That tells you right away, we don't know very much. I come up here and I pontificate about all we know about astronomy. And then I admit, And that accounts for 5% of the matter in the universe, what we think we know. The other 95% we have no clue. We've never discovered what it is. We have evidence it exists. Okay, so coming back to the stuff that we do know exists. Somewhere around 50% of the mass that's in stars is in clouds of gas. So we have, 200 billion or so stars in the Milky Way galaxy, and we have enough gas to make them out about, let's say, 1/7 of that number again. So there's a lot of material, a lot of gas out there that we could use to make stars. Furthermore, when stars die, you're going to replenish gas. So there's a lot of gas out there. We're talking about significant fractions, not just, oh, here's a little, meaningless stuff, even though its density is very small. If that gas is in an H2 region, a region where you have a hot gas that has been ionized because of it, then you can have an emission nebula. If it's close enough to a star or star light that is between us, you can have a reflection nebula. Well, what if it's neither of those? What if we have cool hydrogen that's not close to a star and not in our line of sight? We basically cannot see it. Cooled hydrogen is going to have all of its electrons in their ground state. They are not going to absorb any visible light, so we're not going to see any absorption spectra from them in the visible. Might be able to get a little in the UV. They're basically undetectable. Until in the 1940s, a Dutch, 1944 I think it was, a Dutch graduate student, how much would I love to be a graduate student to make a discovery like this? 44? I don't know. I didn't even think about that when I was preparing.
It's crazy.
Yeah, it's in the right time frame. He realized that we talk about electron spins. I know one of you says chemistry is your favorite topic. And in chemistry, we talk about electron spins a lot. And what people don't realize, but that he knew, because that's what we scientists have known by that point on, is that spin is a misnomer. Electrons don't spin. The electrons have a magnetic moment. That's what they were talking about when they came up with the idea of spin. We've learned that the Earth and the Sun make magnetic fields because of their rotation, along with convection and having conducting material. Well, if you have a charged particle that's spinning, it also will generate a magnetic field. And so they noticed that electrons had a magnetic moment. They behaved like little magnets. And they said, it must be because the electrons are spinning. Hence, an incorrect idea was spawned that a lot of college students still think is true, the electrons spin. Well, what he realized is, okay, if I have two magnets, if they're like this, that's not a stable configuration. You let them go, and one's going to go like this, so that they're anti-aligned. Well, actually, anti-aligned. I think that's right. The magnetic fields are going to go like this. Anyway, you have lower potential energy in one configuration, higher potential energy in the other. Actually, no, it is aligned together as lower. And so there's an energy difference between the two, and he said that energy difference, if you convert that into a photon, remember energy is equal to hf for a photon, that gives you a wavelength, of course, wavelength are related, frequency times wavelength is speed of light, of 21 centimeters. So he predicted that there should be this 21 centimeter radiation from neutral hydrogen when you have the electrons flipping their spin. What would cause them to flip their spin? Well, that's not a very high energy, so some very, it can be visible light, infrared light, would be enough energy to cause the flip the other way. Then it flips back and gives off that radiation. And so these two gentlemen, Harold Ewan and Edward Purcell, were using that beautiful telescope. You see my titles, obviously. Sweet telescope, eh? This here is their telescope that they were using for radio waves. and they detected this 21 centimeter spin flip radiation from the neutral hydrogen atoms. And they got the Nobel Prize for it. It would be awesome to win a Nobel Prize, just for the record. So we have evidence, observation that he was right, that you can have radiation from neutral hydrogen atoms, and now we have telescopes like the Arecibo telescope that will take images to map out where we have hydrogen gas. Now, this picture here is kind of going back. This is showing the structure of a supernova remnant. The H2 regions where you have hydrogen gas that's more than 10,000 kelvins, which will cause the hydrogen gas to be largely ionized, which allows then any electron that flies by to be captured by a proton, fall to a low energy level, and give off emission, making an emission nebula. That's why we have this, but you have some really cool features. Defined filaments there in the supernova. When we learn about supernova, I'll talk about this some more. But this was here just because those hot hydrogen gas regions are likely results of supernovae, actually, that have produced the hot gas, the dark nebula. This is a picture of Barnard 68. The next slide is a picture of Barnard. What do you see there? Nothing. And so first people who saw this said, there really is a hole to heaven. Oh, I keep forgetting. It's bubbled to the top of my mind about 4 times. I have to mention this. The gas that makes up the interstellar medium, I talked about its density, about 1 atom per cubic centimeter. It's like 90% hydrogen gas and around 9% helium gas. And just very trace amounts of anything else. You also have things that we call dust, which has basically a very tiny silicate grain and then some ice on it. Ice being water ice, ammonia ice, methane ice, that kind of stuff. And those little things are much less, like 1,000th of a millimeter across. They're tiny pieces. I just keep forgetting to talk about the composition of the interstellar media. So I got it in there. Okay, so Barnard took a lot of pictures of things like this and helped us to understand what's really going on. In a couple slides, I'll show this picture again and talk about it more. I'm only going to talk about Barnard in one more thing. Okay, he was born dirt poor, didn't have enough money to go to school, got a job working in a photography place where he learned to do photography and to do astronomy stuff. And he became a renowned astronomer with no education. Of course, he was very insecure. I say, of course. Understandably, he was very insecure because, here he is doing this lofty work with no credentials and very aware that all these other people have studied so much and he only knows what he picked up from, not going to school. Mind you, you can learn a lot not going to school. You don't have to go to school to do great things, and he did great things. One of the coolest stories about him is he built a house that he couldn't afford. But there was a newspaper that was offering $200 for every comet people discovered. And he loved observing the sky, so he concentrated and he found comet after comet and used those to pay off his house. So his house is called the Comet House because he paid it off for the money he got from finding comets. Okay, and we will come back to Barnard 68, excuse me. Here's a picture of the Horsehead Nebula. You see the Horsehead right there? It's kind of cool, right? The Horsehead. This is invisible light. Here's the same thing in infrared light. A little different, right? You can still see where the Horsehead is, but it just doesn't look the same. Now, if you want to compare, this is dark. That's the same region in infrared. What's that telling you? If it's dark invisible light, that means that it's not allowing any light to come through it. If it's bright and infrared, that means it's warm, right? It's not piping hot or it'd be giving off visible light. So it's warm, giving off a lot of infrared, but it's thick enough that it's not allowing visible light through from whatever's behind it. So you can learn different things by looking at the same region in different wavelength ranges. And clearly where that horse head is, you have a lot of different detail looking at the two different pictures. This is looking at infrared radiation for our Milky Way galaxy. This is basically going, actually it is going like this, taking pictures that are covering the whole thing and going around a circle. And you see most of the radiation is coming from something close to the center because our Milky Way galaxy is shaped in a disk. Now, as I was preparing for today's lecture, I at least read something saying that our sun's orbit, we're right now in the disk, but we are just passing through. That we're inclined about 63 degrees, it said, from the disk of the Milky Way galaxy. I kind of thought that we were in the plane of the Milky Way galaxy. If we take what we understand about the solar system, we had comets that are in the plane, and then we had comets that are coming at crazy angles. What's the difference between those?
They have longer time.
Okay, they have longer time. The farther away, the longer the time for it to recur. But why do we have the farthest ones are coming at crazy angles and not the closer ones? Traditional answer is the stuff that had formed the solid balls before things flattened out stayed on their original paths. But the ones that were still gas, just the interactions made them collapse with everything else. So the things in the Kuiper belt that are in the plane probably formed later. The things that are doing the crazy orbits formed earlier. And so the same thing would be true for stars, likely. Stars from earlier are doing the crazy orbits. Now, I say likely because there's a lot of other things involved. And we'll talk about that. This here is totally cool, the Pleiades. One of the things you have to point out for the star quiz. Now, I put here an open cluster because it is an open cluster. But if you look at the text there of the caption, it's talking about the kind of nebula it is. What kind of nebula do you see? Okay, now, you may have answered correctly. I'm going to list the three. Is it an emission nebula, a reflection nebula, or a dark nebula? Okay, reflection, because the reflection nebulae are colored. Yeah, blue. Yellow? The reflection nebulae are colored blue, so you say, it's blue, it's a reflection nebula, which means that we have gas that's close enough to the stars that the light is being scattered by the stars and being split out. Okay, back to this. Oh man, it looks once again better on a computer monitor or in a textbook if you have a physical one than it does in the projection. These are two pictures of the same region of Bernard 68. And you can notice that you have the features reproduced. This set of two is this set of two. This and this are, I'm pretty sure it's this and this. I had done all of my alignment stuff before. This is, wow, that doesn't look right at all, but I'm pretty sure. Yeah, okay, let me not do that one. Anyway, I had gone through and made sure, it's the same region. This here looked like an empty void, which is why people thought, it was a gateway to heaven. But with better imaging, we can see an infrared. So this one here is infrared radiation. This one here is visible. We can see that there are stars behind it. The red light can get through a thick cloud better because it's not scattered as much. Remember, blue light was scattered very effectively, red was not. And so if you're going to get any light through a thick cloud, it's going to be red light. And looking at infrared, we can see, there is some red starlight coming through. There are stars behind it, just like you would expect. It's just a thick cloud that's blocking most of the light. So a final slide on viewing the reflection versus dark nebulae. If you have a gaseous cloud that's blocking a star, the light that comes straight through is going to be reddened, and the light that scatters off will be blue. And so depending on how bright the light is, the light that comes through may be reddened but still look white, and you see blue all around. Or you may not see that blue at all, and you just see the very faint red getting through. Believe it or not, this is down to the last, I think, 2 pictures that I have for the chapter. Remember I said we may or may not get through it, and then I went back and did 20 minutes of under lecture. This here is a computer simulation. I put that with asterisks there because, flat earthers talk about a composite image as a computer simulation, and it's not. This here is a computer simulation. This is a calculation of how we might have gas distributed in the Milky Way galaxy. And it has a color differentiated, so the green stuff is neutral hydrogen, and the yellow stuff, it's molecular clouds. Let me talk about molecular clouds. Molecular clouds are where it's cold enough and it's thick enough that you don't have ultraviolet light that can even pass through. So inside the thick cloud where the ultraviolet light can't pass through, it gets really cold, and you start forming bigger molecules. And they found a lot of organics in the molecular clouds. Organics, things like formaldehyde, acetone, things that are organic, by the way, as used by scientists, means things that are carbon-based that are present in living tissues. It used to be believed that organic material could only be created through living things. And then urea was the first artificially synthesized organic material. Now we understand we can make lots of organic materials. Still have lots of problems. Like my wife takes L-lysine. Why L? You have a left-hand and a right-hand version of lysine, as with virtually every other organic compound. And our body can only metabolize the left-hand version. So if you get a racemic mixture of lysine, you have equal amounts of the L and the R, but your body just throws away all the R. So you want the L. The only way we can make L-lysine is by using organic material to start with. If we use something that's already an L, we can produce more L from it. But if we don't have that, we can't. Anyway, coming back to this. This is a simulation of where the gas is believed to be according to a computer simulation. And so you have it spread out in these arms. I'm going to show some pictures later that kind of say the arms may not be where the gas is. This is looking at radiation seen in the X-ray. Now, this is not a computer simulation. This is actual photographs taken by the Spitzer. Oh, no, it's not the Spitzer. It's the Rosette satellite of the radiation that we receive. And that red is X-rays coming from all different regions in the sky, from all different directions. Why? Well, it's kind of hard to tell. The sun is traveling through the Milky Way galaxy. And the sun is in a hot pocket. What I call it here, the local bubble. This local hot bubble is a region probably created by a supernova in the past that has high energy that has made it so we're in a region of lower than average density of atoms. In fact, this local hot bubble has a density that's about 1/100th of an atom per centimeter squared. 1/100th of the average for the interstellar medium. So it's easy going for the sun, right? Except about 10,000 years ago, which is a blink of an eye for astronomy, the sun has entered into this local cloud where the density is 0.3 atoms per centimeter cubed. Almost up to the average for the Milky Way galaxy. Or not for the Milky Way, for the universe. So now we're passing through that more dense region. Interesting stuff. Yes? We call this region where we have this elevated density to 0.3 atoms per centimeter cubed the local fluff. And as the textbook says, don't you like the whimsy of the astronomers with these names? All right, I'm done for the day. I'm done for the week. I'll see you on Monday. Have a great Sabbath.